Okay, quick one for you today. This is problem 3.48 from Morin's Intro to Classical Mechanics textbook, another projectile problem. So here we have a ball of mass m is being launched vertically upwards with some unknown speed. I'll call it v naught. That's actually not known in this problem. And it is observed to rise to a maximum height of L. You might say, why aren't they using h? We're going to use L. So that's the maximum height when it's fired vertically upwards. Now we're going to tilt it so that it's fired along the surface of this ramp that's inclined at angle theta, same initial speed. The ramp happens to have a length also of L, which was the max height in the original case. And the question is, what should our angle be so that we maximize the horizontal distance traveled from the point of leaving the ramp to the same height point, but on the descending side of the parabola. So, I mean, this could be generalized a little bit and say, well, what about the maximum range to land back at the ground, etc. But this is what Morin states, and we might as well keep ourselves a little easy here. Okay, so let's do this in a couple ways. First off, we need to know what this V naught is. That's not given in the problem. I put it in there so that we have some idea of a variable we can use. But what we should probably do is first relate V naught to L. Now that's a basic conservation of energy type problem. So over here in case A, we know that the initial launch energy of the ball is going to be its kinetic energy. And when it reaches the maximum height, there should be no more kinetic energy. After all, it's just being launched up vertically and then comes straight back down. So this should just be mg times that final height, which we'll call L. Pretty easy to see here that that means V naught is root 2gl. Okay, now for the second part here, we're going to go ahead and use a little bit of kinematics. We could do this in a lot of different ways, but I think the easiest way is to use kinematics. And I'm not even going to go to the x and y kinematics separately and try to relate those together. I'm going to do it all in one go by imagining a tilted coordinate system where this direction is what I'll call the, say, s-axis. So not the x-axis, but the s-axis. That's the inclined plane direction. And in that case, we know that the acceleration along this direction is purely due to gravity. There is a normal force, but that's not causing it to accelerate in the x direction. That's perpendicular to it. So I'll call it a sub s. The acceleration in the s direction is minus g, but it's not really minus g, right? Minus g is the gravitational acceleration in the y direction. This is going backwards a little bit. I want to know what component of that acceleration is acting along the ramp. And that turns out to be minus g sine theta. So this sine theta here component is coming from the fact that if I look at a generic point here, I'm going to end up with a gravitational acceleration which is down, but the component that is backwards along my s direction involves the sine of that angle, which is the same as this angle. You could also use cosine of 90 minus theta, and remember the cofunction identity that turns that into sine. Okay. Next, we need to find a way to write down the kinematics relating that initial velocity with the speed when it's just about to leave the ramp. Well, luckily, this is a constant, right? So we know that if we have a constant acceleration, we could go write down some functions involving time, but the way faster way is to use the relation that involves just v's, a's, and displacements. So I'll write that down as maybe v squared equals v naught squared. And maybe I'll go ahead and put s's on here to remind us this is in the s direction, plus 2as times s minus s naught. That is our nice, convenient relationship between velocities and accelerations and distances not involving time for constant acceleration. Now our final speed is what we're kind of looking for, so I'll just call that v. Our initial speed in the s direction actually is just v naught, so that's convenient. That's partly why I want to do it this way, so I don't have to break into components. No sines or cosines aside from the a. A does have a sign in it, and there's an sign also. And then my final S position here, if I start at the origin, is just L. And my initial S position is 0. So very quickly, I can solve for what that final speed is. I'll just leave it in this form. We'll have a minus 2g sine theta times L. And I can also go ahead and plug in our result that we know what V naught is based on how high it went when we launched it vertically. So V naught squared is another 2gl. So overall, I can factor out a 2gl and get a 1 minus sine theta. So that's the speed as it leaves the ramp. Notice that if I have theta equals 90 degrees, then I'd have 1 minus 1, which is 0. So the speed at the very top, of course, of a vertical trajectory would be 0. We already knew that from part A. If theta equals 0, then my speed after reaching the end of the ramp is just V naught. I haven't actually accelerated at all. And then I'll immediately hit the ground. Okay, the next thing we want to do is want to write down what d is, this distance that it'll travel just horizontally from the point of leaving the ramp to the point where it returns to that same ramp height. We could extend this problem, if desired, to ask how far it goes until it lands back at the ground, but it would just involve a little extra trig using what? L sine theta as that vertical height. So let's instead recall the range formula. That distance d is just the range on level ground, really from start to end it is level. We've done this before 1,000 times. Oh, I should not put V naught here though, because notice that this particular V is the V as it leaves the top of the ramp. So this will be V squared. There's a sine 2 theta, that double angle identity, divided by G. Now luckily for us, we already have V squared all written out. The G's will cancel, and I'll end up with 2L sine 2 theta times 1 minus sine theta. Okay, so this is the distance, and we want to maximize this with respect to theta. So we're going to take our derivatives as usual. Okay, we will go ahead and leave this in the double angle form, although at the end it might be convenient to go calculate things in terms of sines and cosines, but let's leave it as is. And we'll take our derivative over here. Call it d theta. The 2L will come out to the front. And then I have a product. The derivative of the minus sine theta here will be a minus cosine. All right, I want to set this equal to 0 to maximize this. The 2L will come away. I don't care about that. Okay, so here's our equation we have to solve for theta. Now, unfortunately, it's a little clunky. We could do some grouping and maybe try to write a sine 2 theta over cosine 2 theta as a tan 2 theta, but we're still going to have some sines and cosines left over. So I think the easiest way to do this is actually to expand out these double angles. So first off, I'll factor this bit to get the cosine 2 theta on its own. And we'll notice, all right, I forgot a 2 right here, but if we factor out the 1 minus sine theta, I guess I could have left in that form anyway, cosine 2 theta has a nice double angle formula. I am thinking about trying to write everything in terms of sines, so I'm going to write the double angle formula for the cosine theta, which is 1 minus 2 sine squared theta. And then over here, when I expand out the sine 2 theta, I'll get a 2 sine theta, and then I'll have cosine cosine. That's cosine squared, which I'm also going to rewrite in terms of sine. Okay, now what we want to do is, first off, let's cancel off these 2's that are in both terms. That's not so bad. And then I've got my polynomial that I want to factor. So I've got a minus sine times another minus 2. That will be plus 2 sine cubed. And then I have a minus is another plus 1 sine cubed. So I'll have 3 sine cubed theta. Now let's look for our quadratic terms. This guy times this will give me a minus 2 I think that's the only one. Now our linear terms, we have a minus sine theta here and a minus sine theta here. That's minus 2. And then finally our constant term is 1, and that's it. Okay, so we've got our cubic equation for sine theta. Now, we already have kind of talked about if I plugged in theta equals, well, 90, so that sine theta equals 1, I know that the horizontal distance will be 0. It's just going to go vertically upward. So that's a minimum. And we know that this derivative is going to find our minima as well as our maxima. So I already kind of know that sine theta equals 1 is a factor here. So let's go ahead and pull out that factor. And then, you know what, I'll go ahead and write it in this way. Now, how do I get the rest? I mean, you could do it by inspection, but it's been a while. Let's go ahead and use synthetic division. So my variable here, I'll call it, say, x as sine theta. And then if I write down this whole polynomial's coefficients, I've got 3, minus 2, 1. And I want to divide out this x equals 1 we know is a root. So polynomial, or I guess this is synthetic division. This is the way I learned it in school. You write down your coefficients, put in the root you're trying to factor out, and then you drop this down, multiply, add, multiply, add, multiply. Oh, look, it was a root. We already knew that. And then I'm left with my coefficients at the end. So we're going to have 3 sine squared theta, and then a plus and then a minus 1. So plus sine theta minus 1, and that's all equal to 0. This last one cannot be trivially factorized, so we're going to have to use the quadratic formula. So our first solution is that sine theta equals 1, but we know that's actually a minimum. So that's when theta equals 90, you're firing it straight up. D equals 0 in that case, not of interest. This bit will give us 2 possible solutions, but we're going to see that only one is physically relevant. So I'm going to take minus my linear term, that's minus 1, and then we're going to have b squared will be another 1, minus 4 times a times c, so that'll be 1 minus minus 12. Right, 4 times 3 times 1 is 12. And then we'll divide by 2a, which would be 6. Now, root 13 is definitely bigger than 1. I don't want minus 1 minus root 13. That would be like either firing it down into the ground or maybe firing it kind of into the third quadrant or something. That's silly. So we're going to drop off the negative sign here. And we'll just get our final answer of sine theta is root 13 minus 1 all over 6. And then to get a numerical value here for this theta, which I'll call theta star, the theta that maximizes this d value, at least in this setup where we're launching it from a ramp that happens to have the same length as the max height, the vertical max height. Let's see, the numerical value I got was 25.7 degrees. And that is the angle that will maximize that horizontal distance.